Hello everyone, just confirming we'll begin the webinar in 2 minutes. Hello everybody, welcome to today's webinar for CLT Toolbox. Today our webinar is the third and final webinar of this specific topic. So today we're going to be covering connection detail design of a post and beam office building for the Australia and New Zealand regions. And today it'll be presented by Adam Jones. Okay, so to kick off, I'm going to take us through a brief agenda. So in a moment, I'll introduce myself properly, and then I'll take us through some housekeeping for today, our latest release, and then we'll get into the design example presented by Adam. So to kick off, I'm Corey Jones. I'm the Customer Success Manager here at CLT Toolbox. In this image, we pictured last week at the IMTC in Portland, which was an incredible conference. It was an amazing event. It was a real grow the pie atmosphere. The industry just sharing knowledge and really collaborating with each other. So it was a really engaged crowd to be amongst and really exciting space. All right, into housekeeping. So I just wanted to make note that the full webinar recordings are now available on the community forum. But we also have some more focused calculator tutorials on YouTube. So if you're wanting to look at more specific problems, we've cut them down into really short, brief videos so you can head to that space if you're on a bit of a time crunch. Some more housekeeping just today throughout the webinar. We've got two different boxes you can engage with. So we've got our chat box. So we encourage everyone to say hello and introduce yourself there throughout the webinar and just to have general chit chat. And then we have also got the Q&A box. So the one with the question mark down below, you'll see that. And that's where you can put in any of your questions throughout the webinar, and Adam will get to all of them at the end. All right, I just wanted to speak to the release. This was a really exciting one in the last couple of weeks. It was a US-Canadian beta program. So we've had a third of the team working alongside this release for the last 12 months, which is really exciting alongside our European product that's just launched. So they've been working really hard and we're really proud of the release that's come. So more specifically, we're doing the CLT floor and wall calculators tailored to US and Canadian standards. We released the timber beam and column calculators optimized for GLT design. I love how we add the Z's for anything American, and we call ourselves American here in Australia by putting Z's instead of S's. And then we've got the compliance with key design standards for both USA and Canada. So there was a lot more that happened in this release, but this page isn't big enough to name them all. There's a lot happening every single release that we do. They're happening every 2 to 3 weeks at the minute, so the software is improving rapidly. Just a little bit more on the beta program. I've got here our expected time releases for each of our calculators. So we've got our basic member calculators, our screw modules, the connection details, the dowels and bolts, advanced CLT timber design, and advanced timber design calculators. So these are the intended dates. So if you have anyone in the US that might want to be a part of our beta program, encourage them to get in touch with us and we'll arrange a meeting with them. We can't go any further without thanking our incredible partners. So our partners that came onto the platform, they're absolutely incredible. Our engineers love designing with their products and we couldn't thank them more. And we just wanted to make note that we have 6 more announcements coming soon. So watch this space. We're really excited to make these new announcements. Before we kick off, I just wanted to speak to the challenges that engineers, or what I hear engineers face, and the reason why our platform exists. So I wanted to speak to 3 hurdles specifically. So the first hurdle and challenge that engineers face is keeping the supply chain availability and variability up to date and keeping codes current. I hear this is a really complex space to be in. The second hurdle I wanted to speak to was the fact that engineers are reinventing the wheel by building their own spreadsheets time and time again and having to keep these spreadsheets up to date. It's a very time-consuming thing for engineers. And then lastly, I wanted to speak to the challenge of education and the lack of education from universities on the mass timber topic. So the reason we exist is to simplify all of these challenges and hurdles, and that's why we're here today. So it's our mission to build tools to enable the profitable design of timber buildings for both member design and connections design. And we pride ourselves on not being a black box. So we're hoping we endeavour to be a platform for all engineers, no matter the level of mass timber expertise they have, to be able to jump on board and design frictionlessly. So without further ado, we're going to jump into the webinar today for advanced connection detail design. So I'm going to pass over to Adam for his presentation. Over to you, Adam.
Very much, Corey, and good morning, everybody. So I could see your screen then, but a couple of people mentioned they couldn't for some reason. So it's a bit of a repeat of yesterday's Wood Solutions webinar, which was pretty funny. But yeah, I'm about to share my screen, but Josh just yell out, and thank you again, Josh. I know you reached out yesterday when we had that challenge. So I'll share my screen. So just confirming, can everybody see my screen right now?
I can see it, and I'll keep an eye on the chat for anyone else that can't.
Keep an eye on the chat, if we can't. So, and just yell out if we can't. So, yeah, today we're going to be looking at the connection detail design. So we're going to go into a little bit more at the, I guess, advanced theory beyond what we had in last month's webinar as well. So, I'll get back to launch the webinar. So focusing at the 50,000 foot level, what is a connection and how does it relate to a building? So if you think about a structure, it's simply constructed assembly of joints separated by members. So on the connection side, you might have a combination of anchors, screws, nails, dowels, bolts, brackets, plates, glue, timber. On the members side, you might have a combination of floors, walls, beams, columns, shear walls, bracing, cores. And then you'll have different materials, whether it's CLT, GLT, LVL, light frame, plywood, concrete, steel, etc. So there's a lot of things going on, and timber having different properties in the 3 directions as well does cause extra complications on top of that. The second point is connections do touch many disciplines that impact the successful design of a timber building overall. So before we get into the structural design, it's always good to zoom out and look at it a little bit of the big picture. So one of the most important things to consider from the start is firstly, design for manufacture and assembly. So there's a webinar by Nathan Benbow, which was really interesting, but what he looked at was how the CNC machine is typically the bottleneck to the actual production of the member as well. So this can be the limiting factor that influences the overall cost of a project. So considering the DFMA of whatever connection you have in mind, it might mean a 2 or 3x difference in the overall cost, even for the exact same connection. So you can see here 4 separate beam column connections with totally different costs based on the connection specified. Second is design for assembly. So if you think about the speed of construction being critical and the crane being the limiting factor, sometimes the specification of a connection can influence the overall hook time, which can influence the overall program and installation speeds that you're going for. So if you are looking for the cost improvements when it comes to this, then designing for assembly is critical. You've also got structural design. So if you think about tolerances, particularly when it comes to different materials, timber does expand, swell or shrink based on moisture, and you might have a different moisture content delivered on site to what it is in service. And then you got elastic deformation as you load it up the building as well. And if you think about that relative to other materials like concrete or steel connections, you might be out of tolerance. So you need to understand how you're designing your connection in relation to this. You've also got durability concerns. So are you actually in an outdoor environment? If you're designing for connections in a wet area, is it corrosion protection and things like that? And robustness as well. So if you think about a connection of a mid-rise or a high-rise building, typically it's required to design for robustness, and sometimes that can be a governing factor when you're doing the design and can actually add to the expense of it all. So you need to potentially consider that. Structural design continued. So different materials behave differently. So if you think about steel compared to timber and how it relates to a connection, a steel beam might conduct heat in the fire, and then that heat can be transferred through the fixing as well to have the charring perhaps start prematurely in the timber, which typically just chars in a gradual rate depending on factors like density and glue and things like that. You've also got fire design and compliance. So thinking about, has your connection detail from a compliance point of view, hopefully you don't need additional fire tests that are unexpected in order to get the connection detail ready for a building. But if you do need those tests, sometimes they can be unexpected and expensive. In other factor in terms of structural design, you've also got seismic design. So thinking about the timber element, it's brittle. The fixing element is ductile typically. So designing for seismic, you want to be on the ductile design and how the timber interacts with the steel. And last month we did touch on compliance, but there are 4 different methods in CLT Toolbox, and each for the Australia-New Zealand context might be slightly different and have advantages. So having the ability to toggle between them can help and mean you're actually doing both the most efficient design. You're not designing overly conservative to save costs, but you're also not missing total gaps in your design method, like might be the case in some design methods. And then finally, in the Australia-New Zealand context, you've got keeping your supply chain options open. So as Corey mentioned, one of the challenges that we look to solve is managing the different grades and availability within the supply chain and how it relates to each other. So for example, you've got different species and timbers within the members side. So say for CLT, XLAM has a MGP 10 on the outers, 6 on the inners. Next timber's got 10s all the way, MGP 10 equivalent all the way through. Red Stag's a little bit different. And then if you go from a European supplier, you're designing with spruce all of a sudden, and that's a different species with a different density. Then on the other side, you've got the connections, the fixing supplier for something like a spline joint. And you've got different properties and different options available. And what is the actual product availability is another challenge on top of that. And when you design to an ETA, having that work dynamically with the density of the timber specified might be important. So, understanding there are benefits if you do back a horse very early, like one timber supplier and one connection supplier, you can get those efficiencies. But having that flexibility and know the options is also has big benefits as well. So at least just having the power to understand the challenges. So in principle, there's a lot of challenges when it comes to timber design. And if you think about one of the most important things we can focus on is getting our cost parity to be better than what the alternative is in concrete. So old technologies like concrete, they're mature, they're at the diminishing return end of the S curve, but we're still very much in this phase where based on certain designs, we can be very expensive relative to the old technology, or we can actually be more cost effective. And if you boil down the mission of CLT Toolbox into a line, it is basically to build tools to enable profitable design of timber buildings. And we're doing all we can to, I guess, bake in that we're actually getting above the concrete options. So that's really what we're trying to do and where we think change is, because if you think about the triple bottom line, sustainability is baked in, human health is baked in, but cost is the variable question mark. And if we tick that box, we can have big change. So 2 principles. One, this is actually one of our company values, but it's also relates to a lot of things. But solve it once, use it many times. If you think about all the complexity in a connection, if you spent 100 hours of consultancy hours into one connection detail and scaled that out 50 times, how much more efficient and, across design for manufacture, assembly, cost, fire, compliance, all those things, you can actually solve for a lot of things through that, versus say if you've got 100 consultancy hours on 50 different connections used 50 times on one project. And think about even just tolerances. Like if you've got a lot of different materials, a lot of different tolerances, it just quickly grows exponentially in terms of complexity. And complexity is something that we're trying to avoid at all costs, to actually make things as simple as possible as well. The second is solve for the bottleneck, also a company value of ours, but very specific when it comes to good design as well. Like if you think about what the big picture is, I shared this same GIF or the same cartoon image as well on, I think, webinar 1, but again, it's relevant. So it's like, imagine rearranging deck chairs whilst the Titanic is sinking. It's a great analogy just to think about what the big picture is when you're designing. So, as an engineer, you might focus on spending a lot of time building a new spreadsheet or designing on the new Eurocode or just working with the bounds of just structural engineering. But the bigger picture might be asking and speaking to the supply chain as early as possible to understand what actual screws are available. And, over time, we're trying to solve that problem as best we can. And also understanding manufacturing capabilities, the fire test data, speaking to the installer, how are we going to enable speed, because those are the things, the big picture things that might actually make the timber project stack up. All right, so that's a bit of high level. Now we're going to go into some of the theory. So this is our third webinar, and we're looking at some new connection details as part of this webinar. So if you think about up until this point, we've done floors, walls, beams, columns, we've done a half lap joint, we've done diaphragm design, we've done a member design, K-bracing, and when we've done a dowel design. So we've gone through a lot of this building. So now we're going to look at a few different connection details, and later in the webinar, we're going to look at bespoke beam column connection details as if you were designing it from first principles. And then you're also going to look at a beam notch as well as a few other things. So there's a lot to get through, and a good place to start is the theory, some of the theory before we actually get into the design. So I've been learning a lot as we've been building our connections. I wasn't a connections expert by any means 12 months ago, but the good thing about our app being not a black box, as we actually uncover education, then it's you can learn as you design. So all these slides are basically embedded in the app in one way or another. So if you think about some of the screw properties and dimensions, you've got length, you got the threaded length part, you've got the inner thread diameter, which sort of like grips the timber, you got the outer thread diameter, the shank diameter, and you got different head types which can be available on screws. So there's different variations of all of these, and this is why you've got so many different screw families within a screw supplier or a connection supplier. Within that one family, you've got different dimensions as well. So there's huge databases involved with different variations to actually find the right screw as best we can. So for our first connection detail, we're going to be looking at laterally loaded connections. So we're going to be looking at the Eurocode. So if you think about the load carrying capacity as dowel type performance, and that's calculated based on Johansson's theory, and it involves a combination of embedment failure of the timber and yielding failure of the fastener itself. So looking at timber to timber, there's 6 different failure modes in single shear that need to be accounted for. The actual equations look like a bit of a mouthful if you're seeing them for the first time, but as you get to understand what are the actual moving parts in each failure mode, you can sort of develop an intuition of designing your connection and designing it well based on what you're going for. So some of the key properties on the timber side, firstly, you've got the timber density. So different species of timber have different densities, and how you actually cut within the timber, you might have different varying grades all the back from the sawmill. And with that, as you actually increase the density of timber, you might get better fixing performance as well. So like I showed you before, as you change the member side of things will impact the connection. Similarly on the embedment strength, so high embedment strength is a timber property as well. And then of course the thickness, so the thicker it is, you're going to improve the capacity on the timber side. Then on the screw side, you've got some important properties. So with the withdrawal capacity, so if you put in, drilled in a screw and then you actually try to pull it out with your hand, the actual withdrawal capacity is the resistance as it's like being pulled straight out. The head pull-through capacity, as the name suggests, is from the head itself being pulled through. Then you got the tensile strength of the screw itself, and then the yield bending moment, so how the screw is performing in bending or resisting lateral loads within the connection. Some other properties, so you got partially threaded or fully threaded screws. So I showed before where the threaded component, so partially threaded means it's threaded part of the way, as the name suggests, and that gives you optimal clamping forces, and some connection details might prefer that. You got fully threaded, so you've got a fully threaded screw, so the threads go all the way, and that gives you improvement when it comes to structural reinforcement or connections under tension. So if you look at the 6 different failure modes and you bring it all together, you've got A, B, and C, which are failure modes in the timber, as you can see in the imagery here. So it's embedment failure of the first or the second timber, and then the second third of these failure modes, the D, E, and F, are actual failure in the screw itself. So the more you actually change the dimensions of the upper timber and the bottom timber and the screw strength or the screw dimensions and the threads and everything like that, it's going to toggle between what's the governing failure mode out of these 6 modes. So as you actually start toggling the connection details in CLT Toolbox, you'll see how these all perform differently. Other important points is screw properties from a environmental conditions perspective. So in Eurocode, you've got service class 1, 2, and 3. The new Eurocode, you've got service class 4. And as you go up the scale, you've got the design to be available in exposed exteriors, and the screw specified will actually be designed in that way. So all the manufacturers will give the ability to actually specify a screw in outdoor environments, for example, where there's higher risk of moisture exposure. But if you don't need to design for that, obviously it's going to be more cost effective to not have those additional layers of protection. All right, so in the previous webinar, we did the diaphragm, we did the half lap joint and spline joints. Now we're going to look at the CLT floor to glulam beam connection detail specifically. So if we look at the design, we're going to be at 8.54 kilonewtons per meter for the design. So we're going to just go straight into the connection detail from the previous webinar. So I'm going to fire up the app, and Corey, please let me know if you can't see anything, but I assume you can.
You're good to go.
Woo! Yeah, thanks everyone watching. We had a bit of a disaster on a Wood Solutions webinar, so we're a bit on top of that at the moment. So if you're seeing this connection, or if you're seeing our app for the first time, as we said, what we do is we build software tools to make it easy to design with timber as much as possible. So we build individual calculators to make each one of those design of an element as simple as possible. So you got connections, you got all these different connection details. But what we're going to look at today is a CLT floor to glulam beam. So we're going to, how about we create a new project? So you can choose your scope if you're an enterprise. We're going to go webinar 3, ANZ advanced connections group. So we'll go level 1 again, and CLT floor to GLT beam detail 1. All right, so as it fires up, we like to, well, as we like to solve it once, use it many times. So as you actually learn how to do one connection detail, as you learn the screw module once of how our app does it, you'll start to become familiar with how it works. So some common things we have is, firstly, you've got top view, section view in both directions. So from a top view, you can see your fixings here. You can see the width of the glulam beam, and we're designing a 4-meter section here for a specific number of screws. And then you got an end distance of 150 millimeters. So that's a top view. If you look at your section view in both directions, you can see the section that we're actually designing. So discrete means a specific 4-meter length, which you can change based on the dimensions here, or alternatively, you can make it a continuous floor section. So it's designing at 1 meter, and then obviously the end distance doesn't matter in this case. So if you look at section AA view, you've always got the ability to do first principles design, but you can also then choose your supplier. So as you change your CLT supplier, for example, everything will work dynamically. And as you change from, say, a radiator pine in our local context with a with a density based on pine of, say, 500 kilograms per meters cubed, if you change to a European supplier based on spruce, the densities will also update as well. Sometimes there's missing properties, and we've implemented a feature. If there's a missing property, it'll pop up for you to input that. So if you've ever had the app feel like it's breaking because a property is 0, that's sometimes the case, because between design codes there are sometimes gaps like that. All right, so let's choose our supplier. We can then choose our, again, manual input, or you can actually choose your glulam supplier again. So let's choose our good friends at Ash alongside a TimberLink Next Timber panel. So these are all available within the glulam supply chain, the mass lam, and again, you change the grades, it will impact based on the fixing design as well. So you can see it here, a CLT floor to glulam beam starting to be populated. Next, you can choose your screw supplier. So for example, if we choose a Simpson screw, you can see warnings telling us a longer screw because we need a longer screw to get the fixing. But again, you can click here to learn more about the screw family. So in a bit of the theory I mentioned before, you can see how within the product families of Simpson, you've got different partially threaded or fully threaded screws, and then you got different combinations with the head type, so cylindrical head, washer head, or a flat head, and each serving a different context, and these having different diameter screws as well, so and length. So obviously when it comes to mass timber, you're looking at a longer screw type. And then finally, the service class based on the moisture conditions as well. And then there's additional notes from the supplier themselves about each to actually understand it a little bit more. So for this screw, we can maybe go with a partially threaded ESCRC screw in this context. Or we can review the rest of the screws here as well based on what property we're looking for. So if we go down, you can get the screw to work dynamically as there, and based on the force, if you got T1 and T2, you can see how the embedment failure might be a little bit different based on the dimensions of the screw. So if we keep going down, you got the analytical method here as an option. So we're currently on the new Eurocode, but if we went to, say, the current Eurocode, you'll be able to actually design to the ETA European technical approval of the supplier as well. But yeah, similar to before, if you actually go through all of the different screw families as well, you can learn about the different families very quickly with our partners on the supply chain as well. And as I mentioned, I think we've got 4 new screw suppliers coming on board, which is really exciting. But again, you can go your partially threaded screws. And then within that screw family, you've got all the different available screws. So each supplier's got some of those nuances as you keep going. All right, so moving through, you got your screw data next. So you got your spacings along the grain. So after we check the forces, we can start optimizing for the spacings. You can actually do a custom embedment length if it's required. So you can embed the screw into the timber, or you can make it flush as well as an option. So for us, if I go back to our forces, we had 8.5 kilonewtons per meter. Not a crazy force. I'll click the more information just so as you go through, you can see what force to tick it into. So it's along the length of the timber, which is an FY value. So 8.5 kilonewtons in that direction, but you can obviously do both directions. Next, you got design data as well. So you got your different partial safety factors and so forth and service classes. So right now, there's one thing we're fixing in the background is this is meant to be green tick. So the calculations are working properly here. We've checked that. It's just showing fail, but you can see the utilization is under 100%. So it is actually working. The geometry check wouldn't be working right now, but we can, not being a black box, at least you can go in and expect that. So you can see the spacings of A1 parallel to grain as well. And you can actually get your spacings right to actually perform the design. So with all those inputs, you Keep moving. So lateral load capacity. So next you've got the 6 different failure modes, like I mentioned before. So you got firstly the withdrawal of timber. So based on the rope effect, you're going to have the screw failing as it yields. You get a little bit of support on the tension side things. So you got the head pull through, you got the tensile failure of the screw, and then you got the minimum of those 3 tensile failure modes, which will help with the rope effect. And then we've got the 6 different failure mechanisms that I covered earlier. So embedment and failure in timber 1, embedment in the second timber, in this case would be the glue lam, joint embedment failure of both timbers if it's a little bit more balanced. You've got plastic failure in the screw in the first timber, which is the CLT, in the second timber, which is the glue lam, and then you've got double plastic failure in both. And you can see how the rope effect is also supporting it. So with that, then you bring it all together, you got the design capacity. So the double plastic failure of the screw is the governing mechanism here. So working at 3.78 kilonewtons per screw, per fastener. But then you have the number of screws that we have over the 1 meter length as well. And then you bring it all together and you can see what we're working at 60 kilonewtons based on the forces that have all been inputted. So 8.5 kilonewtons here, capacity being 14.6 kilonewtons. So I'm going to hit save and I'm going to keep going. And on that red cross, it's something we've got to double check on that one as well. So leave that with us in the background, and that's one of the fixes we can move quickly. But at least as you follow the calcs, you'll know exactly what's going on in all cases. All right, so that was for a glue lam beam to CLT floor. So a few other options that you've got here. You can do intermediate supports like that, or you can do right end supports, or sorry, you can go 2 floors as well. So you can really quickly actually get the design scenario that you're looking for and screenshot that and send it to the drafting person to actually support with the design in that sense. All right, so that's a CLT or timber to timber laterally loaded connection. Next, we're going to look at a steel to timber, a steel beam to CLT floor connection detail. So with this, you've got 5 different failure modes between the screw element and then the timber element. So you've got embedment failure in the timber again. Then you've got plastic failure of the screw in the timber. Then you got the failure modes of the actual of the steel plate and bending in steel plate of the screw as well, or double bending as well. So there's different failure modes, of course, between a steel plate and a screw connection. So again, if we go back to our app, we can find our connection detail here. So CLT floor to steel beam. Finds the webinar that we've already done. So I think we were W03. ANZ Advanced Connection Design. Hopefully we've got 2 of them because I must have been practicing before. Hopefully I think it's the other one. Yeah, I think it's this one. All right, so steel beam alternative. So I think this got released in the last month or so as well. So a CLT slab to steel, and it works in a very, very similar way. And again, you're going to see, say, the top view here. With every release, we just add improvements on how we do our connection details. So you can see a few improvements on the dimensions here with actual cross sections available for section AA and section BB here. So you can see how the steel I-beam's working. Obviously, things like steel angles is next cab off the rank on our side. So obviously, always what design method is available. Current Eurocode A1720 for basic. New Eurocode is your options. I think we went with a Timberlink panel earlier. And again, you can start looking at our cross-section build-up. So let's just go to our thicker cross-section in this case. So you can see it's actually working, or the screw or the dimensions are looking a bit more appropriate here. Let's just choose a continuous floor option, and then the length is out. So you can see a 1 meter strip is being designed for as well. So now you've got the dimensions of the steel beam. So this is basically, rather than actually having the UC sections, we just have this right now as a manual input. So I'll just exaggerate it here. The flange thickness, as you actually input these, the root radius and stuff like that. So if we go, I'll just exaggerate here for the sake of it. you can see you can get everything working dynamically like that, or if it's more like a UC section, everything like that. And then you've got, you know, the geometry checks relative to both sides. They're all calculated, and your beam depths as well. So you should be able to just quickly specify what steel beam that you're actually working with and everything like that, and it'll work accordingly. So next you've got your screw suppliers again. So let's go with a SPAC screw in this instance. So let's see, we've got again the screw families. If you click it, you'll be able to actually see what screws are available from a steel to timber point of view. So we've been working on filtering as well to get that. So the plate screws is one option from Rothelbus. And if you start doing a 160mm screw, it's all working dynamically to actually work out the connection detail. And again, you can design to the ETA of the supplier, and then you can actually see the screw data. So you can see here, the screw position needs to be under 127mm. So if we just go 130, you can see it exceeds the root radius. So you can see it's obviously getting a bit funky there. So we're adding, you know, the ability to actually quickly understand what are the geometries that are required based on the design as well. And sometimes that is different for the ETA versus the design method. You got your spacings, and then you got your options again. So if you go 2 floors, you got your 2 floors here, and sometimes the flange of the steel beam might be the governing factor here. If you've got a UB instead of a UC, for example. So let's just keep it at a right end support. Oh, sorry, yeah, right end support's fine. And then I think we had an 8.5 kilonewtons here, so pretty small load, but again, design data check. So you can see here we're working. So the geometry check as well in detail, and then also the shear capacity check. So your geometries, you can check all the requirements for laterally loaded screws. So again, we go ETA by ETA, code by code to actually have a dynamic working of the geometry checks. Then your lateral capacity. So I mentioned before the failure modes from steel to timber, but again, you got the axially loaded component for the rope effect, but following that, the 5 different failure modes. So embedment failure in the timber, in detail, plastic failure of the screw in the timber with a thin plate, bearing failure of the steel plate, bending and steel plate failure, and double bending. So again, you can read through it and understand exactly how it's working and know, the contribution of the rope effect and everything like that. So that's to work out the capacity or the governing failure mode. And then out of the 5 different failure modes, you can see here what's governing. So right now it's the screw and T2 embedment. So you keep going through, you got the effective number of screws calculated for the lateral load. And you can see we're working here at 12%. So bringing it all together, you can see how it's all been designed in that sense. So if you go in intermediate support, you're still working from a geometry check, but if you went, a smaller flange width, which might be the case for a UB, it's obviously not working right now. So you should be able to design in accordance with the geometries that are required as well. So now I've just got to change the spacings now to get that working. All right, beam depth, flange thickness, web thickness, screw data, screw position. So if you go 50mm, it's working a bit closer like that. We can actually get our section to start working. So geometry check and the shear capacity working again. So that's the steel to timber module. So that's the alternative we had there for the steel beam to CLT floor. Next, we're going to go a little bit further into advanced connection design. We're going to use our individual screw modules to design a bespoke beam column connection design. So some theory on this before we get into it. So we're going to compare the laterally loaded screw versus an inclined screw, which uses the grip of a fully threaded screw, and to see what the difference is, because the axial effect might have, or we'll find, has greater capacity than the dowel lateral effect. So with that, you get a very good interaction between the screw and the wood. So if you think about if you incline a screw, you're actually going from a normal force, putting it on an axial force component as it's actually working on an angle to the screw as well. So old Pythagoras theory to understand how it works. So if we focus on a custom steel bracket, we've got an individual beam column connection here as well. So with a glulam beam designed into a steel plate, and the glulam beam transferring the force in laterally loaded shear of a group of screw connections as well. So we're going to do that for 108 kilonewton loads and have horizontal screws for our first check. So if we go back to our new calculator modules here, I'm going to go ask me later, but if anyone else ever sees this, feel free to just put what you think and then have your comments. So it helps us understand and track our improvement from a user point of view. All right, so let's click a screw design. So we're going to start with a laterally loaded steel to timber. So these screw modules are meant to be available for any time you've got a connection, any connection detail, and be fully flexible in that regard. Go W03, and I think we were this one. Yep. And then we go beam column detail 1. All right, so steel to timber, laterally loaded. It's a little bit like the theory that we had earlier. So we're going to have all the cross sections again. So I think as you learn how to use the software, it'll become more intuitive about how you actually perform the design. So because the geometries and orientations are important here to get right. So for us, we've got a 450 thick timber column in this instance. We're going to go a spruce density of 350 kilograms per meters cubed. Member 2 width as well is 450. So that's the actual getting everything ready from a timber member point of view. We're going to be looking at the steel plate in a second. So choose your timber type, and that impacts the design of the screw. We're going to start with a thicker steel plate initially, and then later, as we optimize our geometries, we can see what the plate that's actually needed. We're going to choose a screw. So go through the screw families, ABS strong. So I think that should be filtered for a plate screw as well. And then we're going to go 10 by 180. So one of the biggest screws in this instance, and if it's not working, we can use what our incline screws impact will have. So we're going to start with the current Eurocode and see if we can get benefits from our draft Eurocode as well. All right, so next you've got your screw geometries. So you can see here the end distances, edge distances. We're going to go 3 by 5 all the way. You can see here we're above what's required for this detail. So later we can maybe tighten up our spacings as well, which will save on the overall plate. So for our load, I think we had 108 kilonewtons. So a bigger load. And we're failing right now in shear. Design data to Eurocode as well. So you got what's familiar there. So if you go through the design check, so we're obviously right now failing in shear, and we can see what happens when we actually improve to the ETA. Now actually, I think we've got a bit of an improvement there, but the geometry check is what's failing right now. So you can at least optimize this, and you can see the end distance is what's required, our spacings as well. And we can optimize this to be closest to what the design is. And you can see here how that's been optimized here. So we can get away with maybe a thinner plate and start actually designing our connection detail accordingly. So we got the geometry check working. So the geometries are working okay. And in the upcoming releases, we're going to actually make the geometries much more intuitive to design by choosing, say, a line load connection or a point connection, and actually filter based on the plate size or the edge geometries and stuff like that. So there are improvements coming in the app from a UI UX point of view. If you look at all the connections here, the 5 different failure modes. So this is done to scale, hence it's a little bit out now, but you can sort of see how it's all the different failure modes. So bearing a thick plate, bending in the steel plate failure, the thick plate, and again with each one. So you can really see how it's failing as well. So design capacity, so you can see what's going through and how it's governing, effective number of screws for the lateral load, and then the overall design working at 159%. And the block and plug failure, so that's within the timber itself, and then the slip modulus as well. So right now we're not failing, but I'm going to choose the same screw arrangement in another connection detail as well to actually see what the impact of a fully threaded screw option is working at an angle. All right, so now we're going to do a beam column connection detail alternative and see what the difference is. So for this, we're going to go back to the app, go to new calculator, go to our screw modules, and we're going to be using the axially loaded component because we are putting it at an angle. It's not using the lateral loaded component. Hence, we're using the axially loaded side grain because it's into the side grain of the timber. It's not into the end grain. So we're going to open this up, and you'll see inside this calculator, you've got the option for the steel option. So W03, searching. Just clicked out of it. Yep, this one, and beam column alternative 2. All right, so we're loading this up. So you got, again, this to an actual beam column connection detail. I think as you get really used to this, you'll see the power of it. So again, we've got a steel plate here, steel to timber. We're going to go side view, timber member data. So as we start populating this, so we are a 450 by 350 member 2 width is always also 450. And we're going to be glulam again. So for our steel plate data, so we're obviously not going to, let's go for a thin plate, 12 mil. You can have the width of the steel plate as well. So let's just keep that at 300 millimeters, and then the offset of the plate along 0. So some of these geometries, as you get familiar with it, may or may not be applicable based on the connection that you're designing with. So again, we'll go to a Eurotech screw. We'll go to a fully threaded screw in this instance. We'll get a 10 mil screw, so let's just keep it at 10 mil by 360. We'll keep it on current Eurocode. Next for our screw geometry. So this is where you can actually start putting the angles in. So if we go 60 mil, we'll see what that is soon. We'll go 5 by 3. And if we start looking at our connection detail as well, you can see essentially how this is currently working. Where's the end distance? So if we go 150 there and 150 there. Oh, so we need a thicker plate for, so I did, just give us a moment. If you click the eye, you'll be able to as well. Yeah, so we're starting to actually design a steel plate in this instance. You can see the side view of our inclined screw members, and that's using the axial component, as we'll see in a second. You got your spacings along both directions as well, which we can play with. So for our forces, we had 108 kilonewtons. And then again, our design data. So you can move through here and you can see we're actually working here based on 108 kilonewtons on 15 screws, or with a 10 mil screw type as well. You can see where we're failing right now. It's the actual spacing parallel to the grain. So spacing along 0. So we're going to update the spacing here. If you go to the top view, you're going to have greater spacing there as well. So I updated that. I think as it's inclined, it is taking into account that as well. So if we go 100 mil, you can have increased spacing, and then now we're checking OK, which is good. It's always embarrassing and high pressure in a webinar when you're looking for the actual geometries to get the design right. All right, so you got the actual loaded screw. So we're using withdrawal from timber and a tensile failure of the screw. So again, it's working in tension in this case. And you take that for the design of the actual component of the screw, and 15 screws for the same force is now working. So you're getting a lot more capacity using a fully threaded screw. So again, you can really quickly design that and understand it with the supply chain, albeit our modules do take a little bit of learning to get it going, and we are improving, I guess, the user experience in the next couple of releases, which is good. All right, so finally, we're going to do a beam notch, and knowing we've got 10 minutes to go, so I'm going to do a 140 mil beam notch here. So let's just say if we were notching into a seated plate connection or something like that, and for the demonstration of the beam notch. So if you go to timber failing modes, we've got, again, our different connections. These are new connections released today. We just haven't done the marketing of it, which I guess we can take offline. CLT design team. Second one, beam notch design. All right, because we've got 10 minutes, I might do on the slightly quicker side, but so it's for our glulam beam notch component. So again, you got a bottom view as if you're looking underneath. So at first glance, it might be not intuitive, but as you get familiar with it, it will be. Section view is probably the intuitive view. And then you got a side view from the other direction with how the glulam beam is facing against the column. So from this view, you can start inputting the notched member. So that's the glulam component, the height. I think we had a 730 mil height using a GL24 European supply. So next you got the supporting column. So maybe an intuitive view for the column. You can see the column here. So currently it's a 200 mil column with a beam that's bigger on it. So we just need to update the column. So it's going to be the same dimension as the notch member as well. So that's from underneath. But if you click back to our section view, we're getting closer to our design. H effective, so that's the size of the notch. So the closer you get to the depth, the less of a notch it will be. So I think I'll go back to my dimensions. We had 140 mil notch as well from below. So if we go like this, I think that was 720 and 580. H effective, you're starting to actually get the glulam as it's actually notching right now into the member. You got notch distance, so obviously the further you go out here, you're designing the spacing that might be based on tolerance or whatever it might be. And you've also got this new component, which is based on you're actually having a slant nut. So always the first thing is to input your dimensions and your properties. Next, you got your design code. We'll see soon if we need screw reinforcement or not. And we can get our forces in. So it's 108 kilonewtons in shear. And then our design, like we see right now, we're failing without reinforcement as well. So it's saying provide reinforcement because we're failing. If you go through all the design checks, you can see, follow them down to see actually how it's being calculated in detail based on the current Eurocode. But we've also got the new Eurocode, which is a method that goes over and above. So, all right, let's just add screw reinforcement. So we've got the screw supply chain again being pulled up. Simpson fully threaded screw. Whoops. Let's go 8x400. And you can see the screw being specified here. And you got a bottom view. So you can see 3 screws for this reinforced section right here. Again, you got your screw geometry, so you got a number of screws. So if you wanted to go to 4 screws from bottom view, you got extra screw reinforcement as required, but let's go back to 2, custom embedment length. And here you can see that we're working. So here what we do is we provide you the design without reinforcement and how it's working with reinforcement in the design. So you can see here we're working with the reinforced section and how much shear is being transferred and how much is being taken by the reinforcement design. So you can always here just turn off the check without reinforcement. We like to keep it in there because maybe during construction or something like that might be important. So again, you've always got the option to go to the new Eurocode as well to see how it's working and it's not working here. So with that, based on the new Eurocode, again, that's the power of this, is you can actually go back to 4 and it's working, and choose what the conservative method is where possible. So we've got 7 minutes. I'm just going to save this, and please, everyone, put in your questions. But one thing I want to show you, hopefully I saved these, but we've got a new print PDF feature. So it does take a few moments to load and render, because there are a lot of, there's a lot of what needs to be loaded per calculator, because it's right now fetching inside the calculator to generate the PDF report. So you'll see that in a second, but you can see here, we're going to have bulk export and import into Excel over the coming releases. That's one of the things the feature team's working on, and then also a one-page PDF. So you can see here the view right now of everything that's been designed so far from a PDF. So you got things like the connection detail working. For our enterprise customers, you'll have your logo as well on the PDF. So if I click export now, that's what gets exported, and you can toggle between what gets exported and not as well. So that's that's one of the things that just got released in the last release, is that little update. So I'm going to go back to the webinar and I'll stop sharing. So Cause, you can take the screen now if you like.
Excellent. Awesome. We'll jump straight into the Q&A section, Adam, just with 5 minutes remaining. So I'll ask you to spotlight the first question once we get to it, once we stop sharing. Awesome. We've got a cool question here up the top from Anonymous saying, hello, Adam, thanks for today's webinars. Can you let us know at the end, how should I currently design anchors, as I believe CLT Toolbox can't do this yet? Great question.
Yep. Yeah, so for anchor design, yeah, we are speaking to some connection manufacturers at the moment to having that in the app. So it is something we're working on. But in the meantime, there are plenty of different options outside our app. So you've obviously always got the PDF design guides of your preferred connection supplier as well, and then you've also got good design software out there. I think Simpson have got a solution, and I think obviously Hilti and Ramset, or whoever you're using essentially. So just traditional anchor design, it's just traditional concrete, which like all engineers, learn a bit more about that at uni, I guess.
Awesome. All right, if there aren't any other questions, you've got a minute or so to get your last questions in, but if there aren't any more, there's only one to go. And that is, do you have anything for how steel and timber behave differently in fire? How can we design for this correctly?
Yeah, so I mean, right now, once we integrate the char modules into our connection details, that will then work out how much embedment you got of the timber for protection of the connection itself. But yeah, the new Eurocode does have an exponential reduction method to actually to determine the reduction in fixing capacity if the fire does reach it, as is the case in some connection details as you go through there. So yeah, it is a complicated topic, that one, and hence sometimes fire testing is something you can't get around all the time. So yeah, hopefully that answers your question, but feel free to reach out.
We've actually got 2 more questions that are coming through the chat rather than the Q&A section. So thank you for asking those. So the first one is, would it be possible to include the effects of density of various wood species in the calculations?
Yep, great. So the first one, yes. So we've got our preloaded densities and properties that we've got, but our enterprise customers, they can add their own properties inside the software. So that means you can add any grade you want and manually configure any density as well. And, so for example, if you chose a new properties for your enterprise, every time you see Glulam, your personally created property will pop up as well. And then that will read perfectly with all of our connection design integrations.
And then the second part, yeah, you're going to answer the second
modes. Yep, of the timber elements under various loads in the grain directions in the toolbox. So I think that's related to our dynamic imagery as well. So I think, yeah, it's a good call, that one. So I think in some of our calculators, like the steel to timber, we've got a a to scale dynamic image of the failure mode, which changes based on the screws chosen and steel. So it looks quite well. I think we do it on some of the timber to timber, but yeah, it's a good point. I think that's something could be cool in all of our connection details, so you can actually see how the failure modes do operate as well. So thank you, Farshid, for your question.
Really awesome questions, guys. So thank you, Adam, for that awesome presentation. I'm just going to attempt to share my screen now. Can you confirm that you can see it, Adam?
Yep.
And the next webinar. So I just wanted to bring the next webinar coming up on May the 7th. So it'll be hybrid CLT and light frame buildings. So we'll be focusing on light frame calculators, CLT wall calculator, CLT compression calculator, and the CLT shear wall. So thank you everyone so much for coming, and we hope to see you all at the next webinar. I hope you enjoyed today, and thank you, Adam, again.
Thank you, everybody. Have a good day.
Bye, everyone. Have a great day.